Welcome to The Explainer. Today, we're diving into something really special, a new kind of AI model that doesn't just learn, it seems to reason in a way that's shockingly similar to our own brains. This could be a fundamental shift in how we build intelligent machines. We see these large language models doing incredible things every single day, writing poetry, debugging code, you name it. But here's the big question that's bubbling up in the AI community. Are they actually thinking? Or are they just the world's most sophisticated parrots, predicting the next word based on zillions of examples they've seen before? Well, a fascinating new paper really gets to the heart of this. It points out a fundamental flaw in today's models. Even though they have billions or even trillions of parameters, their core structure is, and I love this phrase, paradoxically shallow. That fixed layer-by-layer design really limits their ability to do the kind of deep step-by-step reasoning that true problem-solving requires. To get around this limitation, a lot of models use a trick called chain of thought, where they literally talk themselves through the problem. But the researchers call this a brittle crutch. Why? Because one little mistake, one slip up in that chain, and the whole thing can fall apart. What you really want, the holy grail, is what's called latent reasoning. That's where all the hard work happens inside the model, silently and efficiently. Kind of like how you and I just think. Okay, so if the current way of building these things has a fundamental flaw, where do you even start to look for a better design? Well, the authors of this paper looked to the best example on the planet, the most powerful and efficient reasoning machine we know of, the human brain. See, your brain isn't just one big blob of computation. It's incredibly elegant. It uses a hierarchy, where some parts think about the big picture and others handle the tiny details. It works at different speeds, slow, deep thoughts versus quick reactions. And it's constantly using feedback loops to check its own work. So, taking this incredible blueprint from nature, the researchers built something brand new from the ground up. They call it the Hierarchical Reasoning Model, or HRM. And it works just like it sounds. Think of it like a company. You've got the high-level planner, that's your CEO, thinking slowly and strategically about the main goal. Then you've got the fast, low-level worker, the specialist who just hammers away at the detailed calculations needed to get the job done. This structure creates this amazing process they call hierarchical convergence. So here's how it works. The speedy worker just grinds away on one piece of the puzzle. Once it cracks it, boom, it sends a report back up to the planner, which takes that new info and updates the big picture strategy. This back and forth stops the model from getting stuck and lets it tackle way deeper problems than other models can handle. Okay, so the theory is beautiful, right? It makes perfect sense. But you know what they say, the proof is in the pudding. Does this clever, brain-inspired design actually perform any better when things get really, really tough? And to find out, they didn't just throw some easy questions at it. No, they pitted HRM against tasks that are designed to break AI, incredibly complex logic puzzles that require a ton of planning, searching, and, crucially, backtracking when you hit a dead end. And what they found? Well, it's pretty shocking. On these super hard Sudoku puzzles and crazy complex mazes, the big names, models like Claude 3 that rely on chain of thought, they got a big fat zero. Nothing. They just couldn't do it. So the giants of the industry are falling flat on their faces. But then you look at the ARC benchmark, which is a really tough test for general intelligence. And this tiny little HRM model with just 27 million parameters, I mean, that's minuscule today. It just blows past models that are hundreds of times bigger. It's not just better, it's insanely more efficient. Okay, so let's go back to those impossible Sudoku puzzles. Remember that big 0% from the other models? Well, HRM, after seeing just 1,000 examples, solved more than half of them. I mean, the difference between 0 and 55%, that's not an improvement, that's a whole new ballgame. And it's the exact same story with the Mises. Again, where everyone else is stuck at 0, HRM is cruising along, finding the best path almost 75% of the time. This just shows it's not just a little better, it's a fundamentally different kind of reasoner. This is just wow. But here's where it gets really, really cool. It's not just that it works, it's how it works. And to understand that, we need to dip our toes into a little bit of neuroscience. The concept is called neural dimensionality. And don't worry, it sounds complicated, but the idea is actually pretty simple. Think of it as the size of the mental workspace a network has to play with ideas. The bigger and more flexible that space, the more complex and abstract the thoughts can be. So the researchers peeked under the hood of HRM, and what they found was just incredible. It was like looking at a scan of a human brain. The high-level planner was operating in a massive workspace. That 89.95 number basically means almost all its neurons were firing, creating this huge, flexible space for big-picture strategy. But the worker? It was hyper-focused, using a much smaller, more specialized toolset.
But here is the absolute mind-blowing part. Nobody told the AI to do this. They didn't code it to have a high-dimensional planner and a low-dimensional worker. This amazing brain-like structure, it just emerged. The model figured out on its own that this hierarchy was the most efficient way to solve the problems. It organized itself.
And this leads the authors to a pretty bold conclusion. They're basically saying, hey everyone, this isn't just a neat trick. They see this as a real, viable alternative to the way everyone is doing things right now, a path towards something much, much bigger, something capable of universal computation.
And that just leaves us with this huge, lingering question, doesn't it? For so long, we've been trying to build these thinking machines from scratch with our own logic. What if the blueprint was right here, inside our own skulls the whole time? By finally starting to copy the brain's actual architecture, are we on the edge of creating something that can, truly think?